Hello and welcome to the video. This is part 2 of filtering with FPGA using object-oriented design patterns. And last time we did this first order filter object that we then used to create some waveforms that are transmitted to an uart. And in this part we will actually rewrite or refactor the filter to use only one multiplier. Basically, we are going to create a multiplier object which is then going to be used instead of the multiplications shown here. Now, the way the filter works right now is that we have this, if we look at here, we have the overloaded multiplication, which is then used to call for radix 16 multiplication when we actually are using this, or when we wrote this filter function here. And since we are going to create a multiplier object to do actually, if we just split this so we can show, we're going to create a multiplier object to do this. So we're going to first of all buffer the inputs to the multiplier, because at least some FPGAs, mainly Xilinx, uses can actually perform a lot better if we use buffers that are embedded in the hardware multiplication units or DSP units that they have. So this uses just bit vectors or signed data types that to perform the multiplication, and we use 18-bit word length for the multiplication. So what we're going to start out with whenever we do an object is we're going to create a record that holds all of the registers that the object needs. And in this case, we are creating a multiplier record. And what it has is that it has these left and right the inputs or registers of left and right input that are then signed data types of 18 bits, and it has the output register, which is the result in this case, that is also signed, but in this case 36 bits, because the output of a integer multiplication is twice, or actually the sum of the word lengths of the input of the multiplication. As with last time, we also create a constant that holds the, or that can be used to initialize the signal of the multiplier record type whenever we instantiate it. So this is going to be called init multiplier, which is multiplier record type, and it is initialized into others 0, and we actually just copy this 3 times here. We also need the closing bracket. Right. So next thing that we need to do is we need the 4 basic routines that we use any of these objects with. So we need to create it, we need to request the operation, and then we need to wait for the object to be ready, and lastly we will of course get the object output. So the first thing that we're gonna do is we need to create it, so we need to create a procedure called create multiplier. That is a signal of this multiplier record type, so it's multiplier object, which is in, out, and multiplier record type. And in here we will actually just do the multiplication. So actually, first of all, we will in fact take this and add them here, and we are aliasing this. So alias left is multiplier object dot left, and right is alias multiplier object dot right, and the result is alias multiplier object dot result. And what is happening here is we simply put result is left multiplied by right. And this is actually our multiplier here. So next thing that we need is we need to request it, and how we request the multiplication is we call a procedure called request multiplier, and this multiplier, so signal multiplier object, which is out, and multiplier record type, so multiplier record, and then left and right, which are integers, and this is going to be requested so that we actually multiplier object dot left is left, and multiplier object dot right is right. And we actually do need to put here left, so this is to signed 18, as we are using 18-bit multiplication, to signed and 18. So when we request the multiplication with the left and right inputs, what we are doing is we are actually just running or loading the left and right parts for the create multiplier. And next thing that we're going to do is we're going to actually add the ready function. So function multiplier is ready. So multiplier is ready. Multiplier object, and this is multiplier record type, and this will return a boolean. Now here is a bit of a trick that we're going to use, because right now we don't have any method to figure out how many clock cycles it actually takes, or when the multiplication is in fact ready. So what we will do is we will actually add here a shift register that will have equal amount of shifts than is with the, or what is the actual pipeline delay of the multiplication. So this is going to be std logic vector 1 down to 0, and we of course need to add also this here, so we add another 0, and we are missing an opening bracket here. So we will actually add this to our create multiplication here, so that we have shift register that is indeed shifted all the time. So shift register is gonna have shift left -1 down to 0, and we will shift in zeros with every clock cycle. And when we request the multiplication, we're gonna add the shift register, and on the rightmost bit we will actually push 1. So what will happen now is when we actually request, there is no shift register because we don't have alias for here. So what happens here, that when we request the multiplication, we will in fact put in 1 as the rightmost bit in the shift register, and then since the multiplication here, or the create multiplier procedure here, creates the shift, or we actually shift zeros in every clock cycle. Now what this does is that we actually now can look at the multiplication is ready with just return multiplier object dot shift register, well, multiplier object dot shift register left. I have indexed name with boolean. This is 1. So if our shift register is equal length to the pipeline delays of our multiplication, then this will actually add ourselves sort of a feedback, so which we can check for the multiplication to be ready. Which of course simplifies using the multiplier, because we can simply request the multiplication and wait for it to be ready. Now what we need to do then is we need to first add these, or declare these functions so that they can be used outside of the process here. So request multiplication, and then the create multiplication. Also, we still need a method to fetch the result of the multiplication, so we need a function called get multiplier result. So multiplier object, multiplier record here, and we return an integer. And what this will actually return is this one here. So we will shift the result. So alias, we will alias so that we can use the same thing. So alias result is multiplier object.result. And we'll actually put the shift or the radix here as input, so that we can range 1 to 17. So we can actually shift in what, or use whatever radix we want when we actually fetch the multiplier result. And this will actually be here. So now we have a multiplier with which we can use to actually do the multiplications with. So of course, next thing that we're going to do is we're going to actually simulate it. I will do a bit of a bad thing here, because we are just testing the multiplication, and that we will in fact get a signal multiplier here. And once we have the multiplier created, we will actually go ahead and create this multiplier. And when it is actually, let's do so that if simulation counter is higher than 5 and simulation counter is less than 15, then we will request multiplier with the simulation counter and 2 to the power of 16, and if, and we will then create a signal for getting the multiplier result. So that we can actually test the multiplication here. So if multiplier is ready, then we will get the multiplier result. With radix 16 and f. Now we can already run this. And we also need to start the PowerShell with which we can be filter. So here's our GTK wave, and if we look at the multiplier result, we should see it's larger than 5, so 6 to 14. This is actually slightly confusing, so now we should get numbers from 5 to 15. We don't need a new PowerShell, we just need the Python. I will actually just go ahead and take the clean out here. I don't know why I have it. So I don't do that all the time. So 5 to 15. So now we actually have a working multiplier. By the way, if we put here -1 or minus, then they should all be minus 5 to 15. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Good. Also, if we actually put another result here, so this is gonna be result, I don't know, 2, and we will go ahead and copy the others here. And we add 1 here, and then we go in here and put in the result 2. And result is the result 2. So what we did here is we just added another shift register. And if we run this again, this is just to show that we can actually, even though we added just one shift register, due to the fact that we or one extra pipeline cycle, now due to the fact that we actually have the shift register here, as long as the length of it is same as the pipeline cycles, this works just fine. This also allows us to easily pipeline the result outside the multiplier, because we only need to do, actually we can just go ahead and take these out. I don't think we need them. But anyway, now we can actually go ahead and concentrate on making the filter here run with just one multiplier. So how we do that is we actually gonna use a 2 process counters. So we can add a process counter that is an integer range 0 to 7. So we will actually constrain these process counters, and this is going to be process counter 2, and these are simply going to be 7 and 7. And what this allows us to do is it allows us to use a 1 counter for doing the multiplications, and then another counter then to catch the multiplications. Thus we can pipeline the calculation here. So what we'll first do is we will actually take out the if statement here, and we will then create a case statement for, well, the first we need to do actually is we need to go ahead and use this to this. So this is then used to we're going to alias the process counters, and then we're going to use both of them. So the first one we're going to use a case statement for, so process counter here, and when this is 0, what we will do then is we will actually request a multiplication. By the way, we do need to add the multiplier here. So signal multiplier in out multiplier record, and right here we're gonna request multiplier with the filter in and b0. So as we can see, what I commented out, the filter functionality here, we will first put in the filter in multiplied by b0, and the second multiplication will be the filter in multiplied by b1. And we can actually go ahead and run these pipelines. Basically, we can request the second multiplication before the first one is ready, simply because these are not really interconnected in any way. We don't need to wait for the multiplication output for the second multiplication to be for us to be able to do the second one. So we will increment the process counter here, so process counter +1, and we will also do that here. And when others, basically we will wait for start. And we actually forgot to put here. So no, missing create filter. Oh yeah, we do not have the multiplier here. Multiplier record. Like this. So now we have actually done the first two multiplications, basically filter in and filter in multiplied by b0 and filter in multiplied by b1. And then what we're going to do is we're going to use case, and process counter 2 is when 0. So for the first part we will wait for if multiplier is ready. Then we will put the filter out, which is get multiplier result, and we use radix 16, so we put in here 16. And then of course we will increment, so process counter plus process counter 2. So we'll increment the process counter, and we can actually add here the filter memory. So right now we are actually getting this multiplication output, and we will then add the filter memory. Also, we want to actually schedule or pipeline the multiplication here. So what we will do is we will in fact add a variable called filter output that is an integer. And what we will do is we will put the filter output, that is this one here. We'll use it here, so filter output, and we will request a multiplier with filter output and a 1. Now, this is actually one of the benefits of using or putting all of the functionality inside the procedures, that we can actually do this. If we had a variable declared like this, so that it's not initialized anywhere, and it's only used in one part of one state machine, that would actually imply that it is creating a record for the filter output. However, that is not what we want to do. We simply want to be able to use the filter output here, so it's like an auxiliary variable. And inside procedures this can be done because it will not infer any registers to be synthesized. Actually I believe that even the Vhdl standard says that there is not going to be any way for you to create registers inside procedure calls or functions. So variables will not generate registers no matter how you code them inside procedures and functions. So this is actually a great benefit because there is no second guessing. It's completely like obvious that what we are doing here. So this can be used. Auxiliary variables are much easier to use in procedures because they can be used without fear of generating unintended registers. So next part here is that we have now actually calculated this one, and the next multiplication which will be ready is the second part of this. So basically it is this filter in multiplied by b1. So what we do here is we actually just put the filter memory and put the filter in actually the multiplier result. So get multiplier result, again radix 16, and we will in fact increment the process counter again, and then when we have 2, we once more wait for multiplier to be ready, and then the filter memory is gonna be filter memory plus get multiplier result. And when others, we will simply wait for start. So this is our multiplier now. I mean our filter. Now the last part that we need to do is we need to actually add the filters requested here. So what we do is we put here filters requested, and then we will put the filters requested here. So true. And Vhdl again, when we have multiple drivers inside one process, what this does is that the last one will take precedence. So when I write it like this, that it is true and false, unless it is true and true, this will function exactly like that. And this is also like a very simple use for this. Otherwise, if we used an extra if statement, we would have to put an if statement where the process counter 2 needs to be 2 and multiplier is ready, then the filter is true and else it is false. And this way it's a bit more clear in my mind than what is happening, because we know that it is only in this state and at this point that when the filter is done will be set to true. We do need to actually modify our requesting here, because first of all, we are not using the filters requested, we are using the filter or the process counters, which are set to 0. So process counter, counter 2 are set to 0. However, what we still need to do is we need to prevent this from starting when we are not ready. So if filter object dot process counter 2 is higher than 2, then we will request it, and if otherwise we will not. We need then here filter object cannot be read, so we need to actually put this as in out, and we change it here also. Right. So now we should have actually already a functioning filter that is now using just one multiplier. Now if we look at how we actually did it, we have two process counters, basically two state machines. The first one schedules the two first of the multiplications, and the second one then catches the multiplications and actually schedules another one or requests another multiplication for the filter output. Now this is, when coded like this, the filtering is actually done in a fashion that it's calculated as soon as possible. We could also add another if statement here, or Boolean variable that would be set to true when the output is available, but before the filter is actually done calculating. And in that regard, we could use it like so that the output could be read before the actual filter is, or while the filter is still actually doing like updating the filter memory. So we actually don't need the filters requested anymore, so we should just remove it, and our syntax checking should make sure that it will be removed everywhere where I have actually added it. Right. Now we got to the TP filter, actually we need to compile our code for the syntax checking. It should now complain that the filter is not actually functioning correctly, because we are not using a multiplier for it. So what we'll do is we will create a filter multiplier. So actually we'll copy this filter multiplier, and we will actually create a filter multiplier. So filter multiplier, and this will then be used in the filter. Right, so now that the actual syntax checking goes through, so I haven't made any mistakes there, or actually I have made a whole bunch of them, but I have fixed all of the mistakes that I made while typing. This should actually now function correctly. So if we go ahead and take the simulation, actually filter result, output from filter here, it is not functioning correctly, and that is because Why is it not functioning correctly? We have some issue here. This needs to be process counter 2. Also, can we call to one which cleans it, so we need to wait for a few seconds. Now it should work. So, if we add the analog height extensions here and step up it, we also need to add some, actually not here, but in the test bench we need to add, let's say, 350. I need to actually remove the call it without the clean, so I don't do that every time. This is much faster. And now as we look at it, we should see standard filter response. We are in fact actually changing the filter response mid the operation here, and that is why it actually looks more like a second order filter response. So if we just look at this one here, so we set the filter constant, so if we remove this, then our filter response should go back into looking like first order response. So what we will actually do now is, since the application uses two filters, we are going to create another one, and it schedules the multiplication for both of them. So we're going to use filter and filter 2, and we will in fact create the filter 2 here, and we use the same trick as our application does, that we will actually, the filter is ready. Well, first of all, filter 2 here, we will use the output from filter 2, and if the filter is ready, we will request filter with get filter output filter, just filter. Right, now actually we can't use this yet because this filter, we will actually request the filter when the filter 2 is ready, and we need to start this. So if simulation counter is 0, then we will call this request filter and if. So and we will compile the code so we can check syntax. And right now we should have, so that when the simulation counter is 0, we will request filter, and after that, when the filter is ready, we will request filter 2, and when filter 2 is ready, we will request the filter 1. So these two should just loop around, and this is just to start out the looping. So now we can go ahead and compile test our code, and they should now look like a second order filter output. Of course, we need to put some more clock cycles for our simulation, so let's run it to 1300 clock cycles, and if we now look, we see the second order filter response. Perfect. So now what we will do is we will actually go ahead and compile the code, and we will go here and create a multiplier record, multiplier init multiplier, and init multiplier, and then we will create the multiplier and add it to the argument list here. like this. And that should be actually it. So if we look at the previous results, we had 671 logic elements and 6 multipliers, and if we put this to run now, we should see only one multiplier when it is done. Now, although we actually typed in a lot of code, or at least it looks like it, if we look at the diff here, there are only 3 lines of code that we've actually changed in our application here. So even though we actually completely rewrote the functionality of the multiplier or the filter here, we actually still have only a few lines of code that needed to be changed. And even though we actually right now have significant, by the way, how long is it? If we look at the result here, we have the simulation counter. So it's from 13 to 25. And this is actually even two multiplications. So it's 12 clock cycles here. So it takes 6 clock cycles. We have actually six tuples, or 6 times. We have increased the pipeline delay 6-fold, but we only needed 3 lines of code to be changed for that to still remain operational. So the essence here is that we have not changed the behavior, even though we changed the entire implementation, and our code did not change almost at all. If we look at our the diff in our test bench here, it does have a few more lines, but it's because we actually have made a bit of a bad thing, and we are actually running 2 tests in one test bench. And we will actually counter that by creating the filter simulation db multiplier .vhd vunit, and we use the snippet here, and this is multiplier, and we can run it for 50 clock cycles. What we'll actually do is we will go ahead and just move the multiplier to its own test bench. And we still need to create multiplier here. And it's not because we did not add this one here. So now we have actually moved the multiplier to its own test bench, and if we run the vunit, we can see that just a few seconds, I don't know, maybe half a minute or so, and we create a new test bench, and our vunit found the source, and now when we are running all our test benches, it's also running the multiplier test bench. So if we now go ahead and see, this is already done, and if we look at the synthesis results, we can see that we have actually reduced the amount of logic elements we need by roughly 100, and we have reduced the amount of multipliers we need by 5. So previously we used 6 multipliers, and now we can make do with just 1. And we are still running 2 first order filters here. And also, since we did not change the code, how we interface the filters, we are still also configuring the filters on the fly from uart. So if we just first check once the JTAG has downloaded the code, now that it is green, we can actually go ahead and log the result here. And as we run the MATLAB script that actually plots the data from the uart, we can see the result here. So at 5000 as our filter response constant, we have this nice second order filter response, and if we increase it, so raw or decrease the filter response time, actually we decrease the bandwidth, we should get more and more sine wave. Read AD. We should get more sine wave like waveform here. It's more like a shark fin, but since we have only or we have a second order filter, we can see that there is no, well, it's a second order filter response. So also there's actually no real limitation that we need to stick with just 2 filters here. We could in fact go ahead and run a whole bunch more. It's only a matter of how many filters the fitter, or how many multiplications the fitter can actually mux into the one DSP core that we are using. It's probably got quite a few, and this actually even manages better timing than before. If we look at the synthesis results here, I believe it was something like 130 or 125 megahertz, and with our new code we are actually using less logic elements, less multipliers, and it due to the buffering of the inputs, we can actually go ahead and run this at higher clock speeds. So I think that is my video, and I hope that I wasn't going too fast, and this was actually somehow, at least the div here highlights the idea here that I am trying to explain, that since we are using these abstract interfaces to our objects here, even though we heavily refactored the code and create another completely new object that we actually use as the interface for our previous object, or which provides the filter some functionality that it consumes, in this case the multiplication. We did not need to change the actual application here at all, only the instantiation here needed to be changed where we create the objects. And this is actually one of the great benefits of creating these abstract interfaces and this well, what I call the object-oriented design, is that since the interface is defined and owned by the object that we are using, then the actual coding can be done in like higher level, where we actually just define how these objects act on each other. So I will probably do actually a quick video where I just test how many of these filters I can in fact go ahead and run through one multiplier, because right now we are running 2, and I believe that if we added a third one, we could still go ahead and run it through the same multiplier here, and it would not be much of an issue at all. So filter through, filter 3, filter 2, and then filter 3, and filter 3. I will actually pause this video and check the synthesis results after this has done, so we can see, or you can see immediately how it behaves. Right, and now that the synthesis is actually done, we can see that adding another filter, basically third first order filter here, we still match the, or still can achieve timing, and our logic element use is still 660, and we are still using just one multiplier. So even with 3 first order filters, we can still manage with higher clock speeds than with just one first order filter, and even though we are muxing all of the multiplications from every filter through one multiplier. So I think this is the end of this video, and I will actually do a small video just testing how many multiplications we can actually push through that one multiplier here. So thank you and bye bye.